All right, guys, I'm back with a couple of examples on how to first classify the type of molecule, and then secondly, identify the intermolecular forces that relate to physical properties of those molecules. So let's start with a little basic review. You guys know that ionic compounds form between metals and nonmetals. You know that covalent are between nonmetals, but you know that not all nonmetals have the same electronegativity. So sometimes we have polar covalent molecules, other times nonpolar covalent molecules. So really, you kind of have to think back to Unit 12 where we looked at the shape of molecules and identified electronegativity differences to determine polarity. So this is all coming back to play here, and we're going to go ahead and classify these molecules. We'll start with carbon dioxide, which is covalent, specifically nonpolar covalent. And I know this because if you drew the Lewis structure, you would see this is a linear molecule where the dipoles cancel. The next one here, methyl alcohol, has an oxygen. And that oxygen, as you guys know, makes this molecule have a greater electronegativity on one end. And therefore, because of that polar bond and asymmetrical shape, this is polar covalent. Oxygen, obviously, if oxygen is sharing electrons with another oxygen, they are sharing equally. And this is going to be a nonpolar covalent molecule. And then we have nitrogen trihydride. This one, I don't know if you remember Lewis shapes, but this one will form a trigonal pyramidal shape. And because of the trigonal pyramidal shape, it's asymmetrical. And that asymmetry with the polarity of the bonds make this a polar covalent compound. Here's another polar covalent, and I know this based on the fact that it's asymmetrical with polar bonds, and I know that looking at the chlorine on this molecule. We've got another one up here, also polar covalent, polar bonds, asymmetrical shape. And so all of these that I just went over are examples of nonmetals that are sharing electrons either equally or unequally. The next few we have are ionic compounds. All three of these. Oh, actually, my bad. Hydrogen fluoride is not. Yes, it is. Just kidding. It is. It's ionic. Because the electronegativity difference is pretty great. If you look at your electronegativity chart, hydrogen, even though it's a nonmetal, it has an electronegativity of 2.1, and fluorine is 4. Take the difference. You've got an electronegativity difference of 1.9. So that's classified as ionic. Sodium chloride and magnesium oxide are also both ionic, obviously between a metal and a nonmetal. So that's step one when you're identifying the types of molecules. Step two is looking at the intermolecular force, considering that. And so if it's a nonpolar covalent molecule, you're going to have those London dispersion forces, which are weaker. And because of the weaker force, physical properties like phase are affected. So carbon dioxide, as you know, is a gas at room temperature. If it is a polar molecule, no surprise, polar molecules have dipoles, and those dipoles attract. So polar molecules will have dipole-dipole intermolecular forces. Oxygen, again, is a weaker force London dispersion. Nitrogen trihydride would be dipole-dipole. So would this guy. And phosphorus trichloride, also dipole-dipole. Sodium chloride is ion. Magnesium oxide is also ion. Hydrogen fluoride is a hydrogen bond. So when we look at these, we can kind of rank from strongest intermolecular force to weakest. So ion would be at the top, followed by hydrogen bonds, followed by dipole-dipole, followed lastly by London dispersion. And so in the next little video, we're going to talk about how that affects physical properties. Strongest here, weakest down here.